So good morning, everyone, and welcome to this 12th lecture of Memory Design and Test course. And before we start today's session, let us look at what were we doing in the last class. So who will tell me what were we up to in the last class?
Sir, we were looking into mismatches, sir. So basically, what was mismatch and due to which it occurs, and the types of mismatches like random and systematic. In random, also we have seen some like intrinsic, pseudo, and process variation mismatch, and systematic. And apart from that, we have seen systematic mismatch.
So how do you take care of? So someone else now. How do you take care of systematic mismatches?
We can model them, sir.
We can model them. How do we model them? Systematic mismatches, we can model them. Something else that also we can do? Suppose I want to make matched transistors of a sense amplifier. I can model the systematic mismatches, but something else that I can do to improve the matching?
To improve the techniques.
Common centroid layout.
Common centroid layout. Okay. Thank you. What else? What else can we do? Only common centroid layout.
So DFM.
DFM, yes. And आपके project की definition में there is that term used.
Dummy cells.
Okay, yes, good. Environment cells, we don't call them dummy cells, we call them environment cells. Create the same environment. And when you start to create the same environment, we call that as structural matching. When we create the same environment for all the layers, let us say active, poly, contacts, metal one, everything that is critical for us for the operation of that circuit, we call that as structural matching. Those of you who will be working on replica path design, for example, or for replica row decoder design, or for sense amplifier design, you have to take care of all these layout design methods also, so that these mismatches are systematically handled and taken care of. They don't lead to mismatch between matched devices. Is that clear?
So what do you mean by exact same environment? I mean,
what do you understand by same environment?
So like in previous lecture, you talked about in the case of the wires, the density was one of the factors.
Yeah, exactly.
But for the in the terms of devices, what does that mean? I mean, I
that also we saw. How did we give the same environment for the row decoder design? In the row decoder design, we gave the same environment in terms of WP to the devices. How did we do that?
We kept all the NMOSes towards the PMOS.
Yes. Okay.
Yes. At an equal distance from the NVL.
Okay.
Similarly, you can look at stress effects. You can look at all the different systematic sources of mismatch that we talked about, and you can make layouts such that they don't impact the circuit. They don't impact the matched devices, or if they impact symmetrically both the devices equally. Is that fine?
Yes, sir. So actually I had one more doubt. So in the random mismatches, random variations, so we were looking at like various like the lineage roughness and various other factors. So but you also said that we are modeling these variations using the Monte Carlo, right? But in the Monte Carlo, the parameters that the tool varies for the like the VT and the voltages. So like how are these kind of correlated to model
We'll
them?
come to random variations in just a little. First, let us close anything else on systematic variations. Is that okay?
Sure, sir.
Yeah. Anything else on systematic variations that you could do? So what did we talk of? We talked about metal density. We talked about distance from NVELs. We talked about distance from other active regions having similar density, and so on. So another thing that we have to be careful about is any sources of crosstalk. When you design metals, when you do structural matching for metals for, let us say, your sense amplifier, where your small swing signals are coming, bit line and bit line bar, they have a very small swing, less than 100 millivolts or something like that. At that point of time, even a little bit of differential coupling can be disastrous. So all full swing signals that run around or run over the sense amplifier should have equal capacitance with both say bit line and bit line bar, or sense SAT and SAF nodes, whatever the differential pair of nodes it is. Both should have symmetrical coupling with large swing signals there. Okay. And this actually brings us to the edge of random mismatch. So do you realize that coupling like this has a systematic behavior, but the fact that a transition would happen may not be systematic?
Yes,
Are you
yes,
able
sir.
to see this?
So
So this situation is at the boundary of systematic and random. So now let's come to random mismatches. How do you take care of random mismatches? How do you ensure that random mismatches impact is minimized?
Sir, one way can be to select the VT of the devices carefully. Like if we if we know that I'm unable to put it into words, but you can like model the
So let us say I chose a VT of 200 millivolts. What happens then?
dopant functionality, fluctuality, you can control that.
Sorry, Talha, what you were saying something about dopant fluctuations. How do I manage that? How do I reduce the impact of dopant fluctuations?
Sir, you told that statistically doping them, then we can manage the doping.
But how do I design so that there is lesser impact? So, see, Raghav's question was, how do I model it? Your question is, how do I verify it? My question is, how do I design it?
Design like what, sir? I'm not able to get the question.
My question is, what should be the design guidelines so that the impact of random mismatches is minimized? We discussed this in the last class.
The model them statistically.
मॉडल तो अलग बात है ना, पहले डिजाइन. मॉडलिंग इज फॉर वेरिफिकेशन, तलहा है ना. मैं कह रहा हूं एज अ डिजाइनर व्हाट शुड बी द थंब रूल? There was one full slide on that topic to demonstrate that topic. You remember there was a slide on the impact of variations with technology scaling? Hello? What did you observe in that slide?
So that impact increases as the technology scales down, but the impact remains same. So as we go down, the percentage increases, like the basically you are decreasing but the effect remains same. So its effect is more pronounced in thinner gates.
So now, do you have the answer of how to design so that you have lesser impact?
Long channels.
Use long channel lengths. Use bigger devices. The more the area under your gate, the lesser is the impact of variations. Not because the variations don't exist. The variations will still exist, but just that you have changed the base. Just like in plus minus 2 nanometer variation in a 28 nanometer technology is some impact, but plus minus 2 nanometer variation in a 14 nanometer technology has double the percentage impact and a much higher electrical impact in terms of variations. Similarly, if you just increase the base, even though 28 nanometer is the minimum length that you could draw, let us say you draw 40 nanometer. So you are kind of emulating the previous technology's length and reducing the impact of variations now. In fact, that is one reason I actually did mention that in the sense amplifiers and in the SRAM cell, you almost never use the minimum length.
Yes.
Yeah, we talked about that. So for SRAM cell, it also helps in reducing subthreshold currents, but you do not do it also primarily because you want to reduce the variations, impact of variations. So now, Raghav, coming to the question that you asked, that there are so many things: line edge roughness, gate oxide, the interface roughness, and so many things. I do not see any of that in the model that I have. Yes, because all of those variations are clubbed into VT variations. How is VT defined? Do you remember what is the industrial definition of VT that we talked about in DVD course?
So it was linked to the current only, subthreshold current only.
Not subthreshold current. We said VT is the current. VT is the voltage, gate voltage, at which the current of 1 micron per 1 milliampere, 1 microampere per micron width would flow from the gate, from the device. So all these things, whether it is line edge roughness or interface roughness or the range of things that we talked about, they will lead to some change in current of the device. So we model everything as variation in VT and mobility. Okay.
So sir, at the very end, I will only see the VT variation, mobility variation, but the source of that will not be, I cannot localize it, right? That from
Yes. The models, and as a designer, do you need to localize it?
No, sir. I mean, no.
Why put in that extra effort and much more complexity in the device model? Finally, you want the simulator to run fast, is it not? The more number of variables you ask it to calculate, the more time the simulator will take. So you have to keep the models as simple and synthetic as possible.
So,
okay?
most of the time the random variations are modeled using the VT variations, right?
Yeah, VT and mobility variations.
VT and mobility. Okay, thank you, sir.
Okay. So now that we're talking about variations, anything else about mismatch or variations that you have questions about from the last session?
Sir, about the gate length that we were discussing just now. So, sir, if we were supposed to use 22 nanometer and we are using 45 nanometer, then I mean, it's good to use 45 nanometer, right? Then why to actually mention it as 22 and change it to 45 actually?
So in the SRAM cell, you will use 40 nanometer, but everywhere else you could use 28, where variations are not important.
So this is only okay. So even I was thinking that only, sir. I mean, that's only limited to the memory cell itself. The IO and the other things can be done in 20. I mean, like below technology, lower technology.
So right? Everything is done in the lowest technology. Whichever technology you are designing in, that is what it is. We just said that instead of using the minimum length, you use a little larger length. Technologies remain same, Vaishnav. That doesn't change because I chose a larger length.
Yes, sir. Okay.
Are you able to see this?
Yes, sir. I understood. I mean, I was just thinking of this differentiation between the memory. So this the thing which we increase, that's only and like constant towards the memory cell itself, not the outer part, right? So
yeah. And again, don't limit it to memory cell, Vaishnav. I would say wherever variations are important. In analog circuits, you will never use minimum length. You make an op amp, you will never use minimum length. Why?
I mean, so we are supposed to see that all the transistors are in saturation and make
No,
the
you want to
work.
match devices. To reduce the offset of an op-amp, you have to match the devices.
Okay.
It is not about saturation or anything. It is about that you want to match the devices. Therefore, you do not use minimum length. Does a
Okay.
minimum length device not go into saturation? It also goes into saturation.
Yes, sir. But yes, it will go, but the structure would be in such a way that we are supposed to see all the factors that are present.
You can
So-
do that with minimum length devices, Vaishnav. No problems.
Okay, sir. Yeah.
You can always do that. It is mismatch which bothers you, because of which you use larger length devices. It is not a design method specific to SRAMs. That is what I'm trying to emphasize to you. Analog people don't talk about it because they simply say, okay, 100 nanometer length. You don't even question them. Oh, we are in 20 nanometer technology. Why do you use 100 nanometer length? Have you questioned? No.
No,
Why did you not question? Because they simply say, this is how it works. But the reality is, you could do everything with 28 nanometer. Just go and design your folded cascode sense op-amp with this. You could do it with minimum length also. The variations will be very high. To manage the variations and to have good yield on silicon, you say, I will use larger length. That is why I use 100 nanometer length, 150 nanometer length.
Yes, sir. Yeah.
Okay.
Yeah.
So don't assume, investigate and find out.
Yes, sir. I'll do that. Yeah.
Okay. Yeah. So if there are no more questions, we come to today's lecture then.
So,
Yes.
so as you were saying, the technology node will remain the same, but we are using a bit larger channel length. जो channel length होगा वही तो technology node होगा, मतलब उस पे
No.
define करेंगे.
तो इसका मतलब, what you are telling me is that memory cell is getting fabricated in other technology, and on the same die there is a pre-charge circuit which is getting fabricated in another technology.
That's why I got confused. कि
that is what you want to tell me. That is what my question is.
नहीं, वैसे I think technology node तो वही होगा फिर.
Technology node is defined by what is the minimum length, or whatever the node is. There is always a range of lengths that you can use in your devices.
Okay.
Is it
Okay,
not?
that was not clear. Okay.
Oh, so you always assume that for 65 nanometer technology, you have to use 65 nanometer gate length.
नहीं. Yes, sir. I've understood now. Yes, sir.
You always knew you could use larger lengths, no?
Yes, sir.
And the technology remains same.
Yeah. Okay. Yes, sir. Yes, sir.
Okay. So let's look at now statistics of VLSI design. So while we're talking about all these mismatches and everything, it is important to now also see what do I mean by statistical modeling and all that. So I'm not taking this course on probability and statistics. I'm just giving you a glimpse of the kind of statistics that we need to be aware of when we design in VLSI. Again, we can talk about this in so much detail in a memory design course, because memories are most strongly impacted by statistical variations. But as we go to finer geometries, more advanced technologies, even flip-flops and even every other circuit, in fact, has an impact or sees an impact. But memories being what they are, they see the failures first. Therefore, we talk about it in the memories course. We don't talk about it as much in analog design course, because there are trimming bits, there are reference currents which you would trim, and you would bias the circuit again to the desired point. In memories, you do not have that kind of flexibility again, and therefore statistics become very relevant. And in reality, the same statistics you can apply to any other circuit also. The only thing is that those circuits are not repeated as often. You don't need to go to Six Sigma extents, as we will just see. Okay. So what we are talking about when we say talking about statistics is that if there is a Gaussian distribution all of you know what a Gaussian distribution is? What is a Gaussian distribution? So you're searching for the definition of Gaussian distribution. You don't need to do that. What do you understand by Gaussian distribution?
So
Deepak?
it's kind of in nature that certain if it's a random variable, then the certain probabilities are more towards one in, like, it's a density more in middle, and it spreads out as we go from the mean. Basically, as you go away from the mean, the probability reduces for the random variable you are referring to. It happens in nature also, so it's kind of modeling natural something like that.
So when we set out to model natural processes, we see that, okay, I want to target that. Let us say you're trying to hit a dart onto the bullseye. I always want to go into the center, but I may go a little on the towards the left or right or top or bottom or something like that. And since my target is always the center, you will notice that most of my darts would actually hit close to the center if I have a good hand and I have good practice. But there will still be some darts which would go towards the periphery. In terms of processes, for example, we would say that, okay, I wanted 20 particles to be embedded, bombarded, and then diffused in my source drain region. But not always 20 will be there. At times 21 will go, at times 22 will go, at times 18 will go. So these are variations that will naturally happen in any manufacturing process. And Gaussian distribution models such variations well. Okay. But Gaussian distribution is not the only distribution that we are worried about in VLSI, but Gaussian distribution is the primary distribution because of which our mismatches are introduced in our circuits, in our devices, in our designs. So, for example, we talked about gate oxide thickness. That, okay, there will be places where there will be 2 atoms, there will be 2.5 atoms, or the orientation is such that the gate oxide thickness would vary from 22 to 28 nanometers. That was the micrograph that we saw in the last class. So in reality, since the target was, say, 25 nanometers, most of the samples will be around 25 nanometers. In fact, if you plot the distribution, the probability distribution of the thickness, you will see that around 25 nanometers, that is the center of this curve, there will be maximum number of samples. So let us say this is 25 angstroms, the gate oxide thickness, and up to 68%, 68.2% of samples would exist between plus minus 1 sigma. Let us say sigma was 1 angstrom, so 26 angstrom and 24 angstrom. So between 24 angstrom and 26 angstrom, you would have 68% of your samples. Between 23 and 27 angstroms, you would have 95% of your samples. Between 22 and 28, the measurements that were shown on that micrograph, you would actually have 99.7% of your surface area having that kind of a range. But there will still be places. Which would correspond to this remaining 0.3%, where thickness could be less than 22 or greater than 28. Do you get the sense of it? That as you go beyond the nominal, the mean point, the number of samples you will get there would reduce. Have you noticed this in your experience also? Hello?
So as we are moving away from the mean, the number of samples are reducing.
Yes.
Yeah.
Have you experienced this?
Yes, sir.
So when we say that SNM is 6 sigma qualified, what do we mean?
It means that we are allowing, I'm like 99%. I'm like, it's the best case. I'm like, we have this gap of 6 sigma, which consists to the 99% or 99.7%.
Okay. So actually, the 6 sigma, like some of you might have heard, those of you who have worked in the industry for a little while, you might have heard the term 6 sigma approach. Have you heard that?
Yes, sir. Yes, sir.
So this is the 6 sigma that they talk about, plus minus 3 sigma. That is the 6 sigma that management approach talks about. However, when we talk about SRAMs, when we say 6 sigma, we're talking about 6 sigma on this side, one side. And we want to ensure that this nominal minus 6 sigma is also a SNM value which is acceptable to you. Why do we need to go that far?
Increase yield, sir.
Increase yield.
There could be many variations. So we need to accept many. There could be many variations. So we need to accept many.
There could be many variations. But
there
there
are
is
many
6 sigma way. Just look at what is the probability of getting something there. 99.7% are within 3 sigma. Why do I need to go to 6 sigma?
So, but there are many cells. I mean, like 1 MB could be meaning 1 billion.
Yeah, 99.7% means in 1,000 cells, how many would not fit?
3.
3
Three
cells.
cells.
3.
So in every 1,000 cells, 3 cells would fail. Is it acceptable to you?
The chip would fail. So no.
No. Now, is it acceptable for a management situation? How many projects does a company do, or how many projects does a team, any particular team would do in a year?
20.
10, 20, depending on the size of the projects and the size of the team. Now, 20, what is the probability of failure happening within those 20 if you are qualified 6 sigma of the management approach? If you qualified from this to this, and you have only 20 samples to take, the probability that particular sample will come out of range is much lower, na? Since the number of samples in those management principles or on management practices is lesser, they go to 6 sigma, which means plus minus 3 sigma. Since the number of samples that we have to account for in memories is much, much higher. Suppose I want 99% yield with a 16 megabit capacity. What is the failure? What is the number of failures that are acceptable? So you will see that for a 16 megabit capacity, I need to go to 6 sigma extent to ensure a 99% yield. Because 16 MB means 16 into 10 raised to power 6 into 100. So these many memory cells we are talking about, 100 dies. And of this you say one should fail. So there can be only one failure in these many samples. And that you will see means so many 9s before you get a first 8. And that is why we need to go to plus minus 6 sigma analysis in our designs.
So we are talking of one die out of 100 dies, or one cell among all the cells?
You tell me. Can this one die or automatically fail? One cell fails in any one die. That die is waste, na? If you want 99% yield, what are you essentially talking about? You are saying that in that 16, not 16 megabit, in that 1600 megabit capacity, which is across 100 dies, one cell fails. Now, in that same die, there could be another cell that is failing. That will not lead to any additional loss of yield. But again, what is the probability that the second failure will also lie on that same die? 1 by 100. Is it not?
Yes, sir.
So, for all practical purposes, you can only accept one failure per 100 dies. So this is the kind of capacity in which I want only one failure.
So So can you give an example? I'm not clearly getting the concept. Like,
okay.
So I understand the Six Sigma part, but why we have moved from 3 Sigma to 6 Sigma? Is it just because the yield?
So let us say you designed something with plus minus 3 Sigma.
Yes. Yes, sir.
I have one megabit memory capacity on the chip. One chip.
Okay. Yes,
how many memory cells do I have?
1 into 10 to the power 6 into 100.
On one chip.
Yes, sir.
1 into 10 raised to power 6 is what I have on one chip, na?
Yes, sir. Yes, sir.
So, agar 99.73% is the pass rate, how many cells on that one chip will fail?
99.73
is the pass rate for that design. How many cells in that particular chip will fail? One chip only, abhi.
How many cells?
So if this is the pass rate, what is the failure rate? What is the probability of failure? If the pass rate is 0.9973, what is the probability of failure? 0.0027?
Yes, sir. Yes, sir.
So if every cell can fail with the probability of 0.0027, a collection of 1 million cells would fail. How many of them would fail in this setting?
1 million and 2.00027.
0.0027. So that would be equal to 2700 cells.
Yes, sir.
Every die will have 2700 failures. What yield are we talking about?
Okay.
So is it just about yield, or is it just about getting something out functional?
Yeah. Yes, sir. Yes, sir. And in Six Sigma, the number of dies the number of cells which are failing are less.
Obviously, anything that something. So if we are qualifying plus minus 6 sigma, we are ensuring that 99.9999998% of cells are taken care of.
Okay. Okay, sir.
Only remaining are outliers. And in that also you will see every 100th die there is something failing.
Okay, sir. Yes, sir.
Sir.
Yes, Vaishnav.
Sir, I understood this Six Sigma thing, but sir, this is okay for the 16 MB example. This is fine, sir. I mean, one is getting failed. So, sir, but we even design the memory in like GBs also, right? So, in that case, I think 6 Sigma is also not sufficient. I mean, we are supposed to go to 9 Sigma.
No, for there, then we will go to repair mechanisms.
So,
we'll talk about repair. We'll talk about repair. Don't worry.
Okay, sir. Okay.
But yes, when you verify your designs, you have to verify it for 6 Sigma. Plus minus 6 Sigma. Not the management wala 6 Sigma. Okay?
So, but like you're saying that even in one die, even if one bit cell fails, my whole die will fail. But sir, like I will have kind of I would have modeled or designed something na, if my bit cells fail, there are some like other bit cells which can take place of it, or we can use it.
So
I mean,
we've not talked about it yet, not Raghav. So for present understanding, a die, even one cell fails, the die is rejected.
Okay.
I'm already telling you we will have some repair. We will talk about repair, not today, probably next class. But if there was no repair, then the die has failed.
Yes, sir. Yeah, one cell fails. Yes, sir.
Sir,
yes, Vaishnav.
Sir, knowing this bit scrambling, is that like repair mechanism, sir?
We'll come to it when we talk about bit scrambling, repair mechanism. Is that okay?
Yes, sir.
So what we are saying is that we have to qualify plus minus 6 sigma. Now let us talk about two additional numbers. What is called as process capability is defined by a number called CP and another number called CPK. Okay. Both CP and CPK have different impact or different convey different kind of information about the process. The first CP indicates that the statistical control in the process is good. What do we see? What is the upper specification limit minus the lower specification limit upon 6 sigma of the process? We will just look at what this means. Okay. And CPK instead talks about a different parameter. It says how far is my upper specification limit from the mean and how far is the lower specification limit from the mean. And then you look at it in terms of sigma. Now, what does this mean? Now, process capability means that if your CP is less than 1, if your CP is less than 1, what happens? What it means is upper spec limit minus lower spec limit is some value, but your 6 sigma is crossing that value. Are you able to see this? If this is equal to less than 1, means that that your design is crossing this upper spec limit and local spec limit. Therefore, it is less than 1. CP equal to 1, exactly equal to 1 means that plus minus 3 sigma of my curve lies within the specification limit. So the failure rate would be 0.3%. See, what did we say? That plus minus 3 sigma ke beyond, there could be 0.3% number of samples. That was what we just saw. Hello?
That was 0.03, I guess. 99.97 था ना वो.
99.97 था. 99.7 था.
Okay. हाँ, okay, yes.
1000 के अंदर 3 failures होने थे.
Yes,
so 0.3% is samples will still come out of it. That is CP equal to 1. What does CP equal to 2 mean? CP equal to 2 would mean that each side I have 6 sigma extent which is taken care of. That is where I said that CP greater than 2 indicates that the process is in good statistical control. You can think of getting good yield on the memory. Are you able to see this?
So CP is equals to 2 will be our 6 sigma limit plus 6 sigma and minus 6 sigma.
Yes.
तो CP is greater than 2 वाला हम उसको good क्यों बोल रहे हैं?
क्यों? आप बताओ. उससे
अच्छा, और ज्यादा कर रहे हैं. Okay. Yes,
I'm
sir,
qualifying more than what was minimum required
yes,
for the exam, na?
Yes,
it's a
sir,
good process.
Okay, sir.
So now that is about process control. Now what does
anything greater than 1 is also good, right?
Yeah. है ना? So now
why are we going?
Sorry.
So why are we going for CP greater than 2?
We will just see. Just wait 2 minutes. Let's look at the other parameter which defines process capability. Let us say that I actually have this CP equal to 2. So I have this kind of a Gaussian which is plus minus 6 sigma on each side. But in reality, the process may change, may shift a little to the left, a little to the right. The typical process corner is centered right away on the target. But slow and fast process corners are also there. Is it not? So the slow and fast process corners would be here. Or could be here, as they have shown. What does this mean? Suppose my slow corner is here. What does this mean?
So that means that in the lower one we are going even beyond minus 12 sigma, minus 6 sigma on the lower side, but nothing on the positive side is covered.
Yeah. So what this means is that all these cells which are on this side of the lobe are getting failed, are getting rejected. So for the SS lot, for example, my yield is 0%. 50% only. Is that acceptable?
No, sir.
No. So the other parameter talks about process capability in terms of how the centering is, how good the centering is. It's capable of producing repeatable products. How well can I center it? That is what CPK talks about. Now let us say you kept the CP equal to 1. Or you kept CP exactly equal to 2. What happens? As soon as CPK degrades, what happens? As soon as CPK degrades, you notice that your memory yield goes for a toss. Because for memory to function well, you want it plus minus 6 sigma. Therefore, you would ideally want CP to be greater than 2 and CPK to be less than 1.33. It only leaves more margin for you and allows you better yield. Is that okay? Hello?
Yes, sir. Yes.
So the values of CPK, sir, the 1 greater than 1, can you elaborate on that, sir? And then
So what is the definition of CPK? Let us look at it. How far is my upper spec limit from mean, or how far is my lower spec limit from mean? So what is happening here? What is my, suppose this is my mean, just before mean, before the lower spec limit. It is not even 1 sigma away. What is the value of CPK? Less than 0.33, na?
sir, I mean the upper spec limit would be the value corresponding to minus 6 sigma or the plus 6 sigma.
If it was centered in there, na? Spec limit का मतलब क्या है? चलो, tell me this. What do you understand by spec limit? अगर वो ही नहीं समझ में आएगा तो how will you understand what I'm talking about? What is spec limit?
Upper and lower bounds for my design for any parameter.
Upper and lower bound. If you violate these bounds, then I would reject the die. है ना? So when I had my process centered here, in between, right in between upper and lower spec limit, I said that my CP is equal to 2, let us say. So plus minus 6 sigma touch the limit. How many failures are we talking about? Very few. 99.9999998% is passing. So very few failures. But now, due to process variations, systematic variations, the length is made a little longer. So my devices are a little slower. When my devices are a little slower, let us say this curve shifts a little to the left. Now what happens? My mean is now closer to the lower spec limit. Are you able to see this? So my CPK, which was 2 initially because mean was 6 sigma away, 6 sigma by 3 sigma is 2. So it was 2 initially. If it is now just 3 sigma away, it has now degraded to
1 sigma. 1. Yes, sir.
And at that, you realize that there will be yield loss.
Yes, sir.
22%,
23%.
Some yield loss will start to happen. That is why you want CPK to be less than 1.33. Greater than 1.33. Okay? So this is what it is. This is what it means. CPK equal to 2 and CP equal to 2. Very well centered process. In the center of it, good yields. CP equal to 2, so the process control is very good. Random variations are few, but systematic variations are higher. CPK equal to 0 means you've gone for a toss. Even though your process control is very good, random variations are very well controlled, but your yield will only be 50%. Because 50% of the dies are beyond this upper limit. Are you able to see this?
Sir, confused regarding which one refers to random and which one you're referring to static.
So CP refers to random. That says what is the extent of these local variations there. CPK refers to where is my lot position. So this could be the lot positioning part.
Yes, sir. But I got confused because you mentioned the example of length, which we use actually to control random.
Oh, but all devices have like get etched in terms of poly etching happens simultaneously, is it not?
Yeah.
So if poly etching is done simultaneously, then if, for example, you etch the particular die for 1 millisecond more, what happens?
Length reduces.
All the devices will now be towards fast.
Yes, yes.
So length variations, these systematic length variations would lead to systematic shifts.
Got it.
Now, there is also line edge roughness.
Mm-hmm.
That will be minimized if you use large length devices.
Sure. Got it.
Okay.
So basically, CPK is, we can imagine them as FF or the global variations, and they are
how far away from FF lot or something is your upper spec limit or lower spec limit?
like the small circles we imagined in the rhombus last semester.
Yeah.
They are the CP and then CPK are those.
Yes.
Okay, got it.
Okay. So now till now we're talking only about Gaussian distribution, and that is actually the most common distribution that you will see. However, in reality, in VLSI, you will also see log normal distributions. You will see Poisson distributions, and you will also see Weibull distributions or extreme value theory being applied to various parts of VLSI design. Okay, each of these distributions could be of interest to you depending on what project you are working on. Suppose you're working on leakage control, then I would say you have to be a very well aware and you have to take care of things by using log normal distribution. Suppose you're talking about gate dielectric breakdown, then I would want you to work with Weibull distribution and extreme value theory. But as VLSI designers, if you want to do some research and do some good design work also, it is important that you are comfortable with some of these very few but very important distributions that are fairly evident and fairly commonly used in VLSI design. I heard a sir sometime, so there was a question. Please ask.
Sir, so this CPK thing, sir, if that's 1.33, I can see, I mean, like if I calculate, there is around 30% of loss or 33% of loss during the worst case. So shouldn't that be CPK should be greater than 2 then?
Yeah, for SRAMs, you want to put CPK greater than 2. Yes, you can say that.
Okay, sir. Okay.
But you will see that to make such kind of a process control, the complexity and the cost of the process increases. Therefore, we will talk about repair also.
Okay, sir.
Okay. Yeah.
Sir, is this Six Sigma only for memory or everywhere in all the chips VLSI use Six Sigma variation?
So you tell me.
I want everything to be Six Sigma, but it is difficult to design having this.
And it's not even required now, Aditya. Suppose someone tells me that there are 500,000 flip-flops on a particular die. I know 5 sigma would suffice. Why do I go to 6 sigma?
So we design on the quantity, like how big is it?
Yeah, but we have to realize that depending on how big the die is, depending on how big the design is, the number of times a cell is repeated would increase. And that is what should guide you to decide whether you want to go to 6 sigma or 5 sigma or 3 sigma is sufficient. Okay. So do not rectify it as a rule. It's not a rule. I have gone through all this pain of explaining the statistics to you so that tomorrow, if you come to some other thing, you are able to decide how many sigma to qualify there. Okay. Don't rectify it as a rule. Raghav?
So like in the with the CPK, we are modeling the lot basically. Say if I have the fast lot, so I will get a certain mean.
Again, please don't get fixated with just the lot. Even in slow lot, even in typical lot, Do you think that lot just gets, a silicon would come only on slow lot or typical lot? No. If I say this is the rhombus, this was TT, this is SF, this is FS, FF and SS, do you think that only these 5-6 points would exist? No.
No, sir.
Entire range would happen. You saw, remember the ellipse that we're talking about, that we saw in the DVD course also? This is an entire range in which something would happen. So lot mat karo. Zyada mat faso uske andar, FS or SS ke andar.
So actually the question is ki, then what exactly, like, I mean, able to see the impact that the CPK has a different, what I see in CP, but when we would be modeling, say, Monte Carlo, then what does Monte Carlo has control over? Does it shift the mean also, or does it only considers the sigma variation? I mean,
It depends from, it changes from tool to tool, Raghav, and it also changes from fab to fab. Some fabs would say that, okay, I will model the entire, all the lots and everything, all the variations in one simulation itself. That is called as global variations. Okay. At another time, you may say that, okay, I would want to qualify all the lots. So I will run Monte Carlo on all the lots separately. So I will qualify all these regions by myself. So that depends on your design methodology. You could already bring in the lot variation and then say, I will only see the variations of CP. Or you would say that, okay, I want to see variations due to CP and CPK simultaneously, and you would do a global simulation. It depends on methodology that you want to use for your verification and whether the models that have been given by the process teams, they support it or not. You can do both ways.
And so similarly, the definition of how much sigma should I qualify will change also depending upon this event when I choose the global or these kind of.
Yes, you can always modify that, but yeah, it has to come from a good understanding of probability and statistics. Don't just randomly say I will qualify 3 sigma only because I'm here. Look at how many samples are we talking about on chip, and what would be the marginal yield loss because you qualified only 3 sigma and not 6 sigma when you were on the slow lot. Okay.
Okay, sir.
But you can do that, yes, as a designer. See, if you notice, my endeavor across DVD and even MDT is to turn you into good designers, circuit designers. So I'm telling you all these levers so that you know that there is this flexibility that you can use as a designer. Okay. But again, do not get fixated. I'm giving you the concepts. I'm giving you why something is done a particular way so that you do not accept anything as a thumb rule or as a rule, as a something which is written in stone. I'm not giving you any dictats. I'm just showing you the path. Then you travel the path whenever you need to. Okay.
Okay, sir. Thank you, sir.
So where all do we need to look at mismatch in SRAMs? We already talked about these things: stability, SNM, right margin, right time, read current. All of those places we look at mismatch. When those of you who are working on sense amplifiers, we would want to look at the mismatch of or the distribution of offset. We would like to look at the distribution of output delay and so on. So mismatch is something that we will play with a lot when we are working on memory design. Even when you're working on analog circuit design, for example, ADCs, DACs, PLLs, anything, you have to take care of mismatch. But in SRAMs, there are some places which you definitely need to take care of it. Okay. So these are about circuit level analysis. All that we're talking about is SRAM cell or a sense amplifier. So these are small circuits. But a memory will be functional not only when these small circuits are functional, but also when you always have the right kind of architecture so that SAEN arrival is at the right time. You remember this diagram where we said that, okay, when the word line is selected, the bit cell will discharge and differential will appear at the sense amplifier nodes. You remember this? What we want to say is that this SAEN should arrive at a time so that the minimum offset requirement of the sense amplifier is always met. Hello? You remember this constraint that we had?
Yes, sir.
How would you meet this constraint? There would be a memory with 100 rows. There would be a memory with 500 rows. There would be another memory with just 42 columns, another memory with 112 or 128 or 1K columns. How will you ensure that whatever the memory size is, SAN arrives at the right time and not earlier or not later? So what happens when SAN arrives later than the desired time? Sorry?
So if SAN would arrive later, then maybe the clock goes low and the word line clock goes, and we do not because basically everything would become high Z or something unknown state internal nodes. If it
So yeah, see, SAN arrives along with reset. So when SAN comes, at the same time you start to reset the word lines, you start to recharge, pre-charge the bit lines and so on. So if SAN arrives late, it means the reset of the memory has been delayed. It means the overall cycle time of the memory goes for a toss. If SAN arrives early, what happens? And in that case, there is not the required mismatch, or there's not the required differential voltage at the sense amplifier inputs, and due to mismatch, your read operation can fail. So you do not want SAN to arrive at very distant time from the optimal time. Are you able to see this? Hello?
Yes, sir.
So what you want is that when it is a large cut, let SAN arrive late. When it is a small instance, let SAN arrive fast enough. So to do this, what is done is that in the memory, we add what is called as a replica path. This replica path, what it does is it tracks the worst RCs for both word line and bit line, and then generates enable signal there. Okay.
So sir, that means the cycle time is controlled by the worst case bit cell here.
Not exactly the worst case bit cell, the worst placed bit cell.
Place, that's what I meant. Yeah, place, the corner one.
Yeah, not the worst case. The worst case cell could be placed anywhere in the memory. The worst case cell could be here.
Yeah, sorry.
I don't know. But
Sorry.
the worst placed cell.
Got it.
The most distant placed cell. So yes, you're absolutely right in that, because I want that whatever cell is here, if this was also the worst cell, even then my memory should work. So I at least bring my replica paths, my word line and bit line RC should match. Okay. And then notice that I select more than one cell over here. Why do I need to select more than one cell over here? So those of you who were in the office hours yesterday, they should be able to answer right away. Raghav, you have a question? Your hand is raised. Okay.
We have to get the digital requirement to enable sense amplifier.
Yeah. See, the important thing is you cannot really have a sense amplifier on the replica bit line. If you make a real sense amplifier here also, then where will you bring its trigger from? You're stuck in the same loop. So what we say is we will put a inverter kind of sensor or something else, something which does not require an enable signal for itself. We will put something which would convert, which would sense that my replica bit line, let us call it as rep BL, has discharged, and now I can trigger sense amplifier on. If my replica BL has discharged enough, I would say that my actual bit line has also discharged. Let us say I want to discharge my actual bit line by 100 millivolts. And let us say the inverter over here trips at 300 millivolts, and I'm operating at 1 volts. How many cells should I put here?
Seven? No, so three only.
No. It trips at 300 millivolts, not 700 millivolts, not 300 millivolts below VDD. It trips when replica bit line has gone to 300 millivolts.
Oh, then 7.
Are you able to see it, everyone? I need to discharge replica bit line by 700 millivolts so that when SAN goes, it intercepts this particular bit cell or any bit cell at greater than 100 millivolts. To be able to do this, because they're the same cells that I have put in the replica column, I need to put at least 7 cells in the replica column, which would discharge. In a real array, only 1 row gets selected. Over here, I say that 7 rows should get selected.
Sorry, sir, I could not get. Can you repeat?
What did you not get?
Sir, 7 cells selecting, sir.
So the discharge rate of this cell and this cell is same. They are replica cells, same cells have been put at both the places.
Sir.
Now you want the actual bit lines to create a differential of 100 millivolts. But you want the replica bit line to have a differential of 700 millivolts. In the same time, how many cells on the replica bit line should discharge?
7.
Is it okay?
Sir.
Huh? Talha, is it okay now?
Sir, I will. No, sir.
No, not yet.
No, sir. Why is 700 millivolt there?
Because that is how I tuned the sense amplifier of the replica bit line. That is when I will trigger the SAEN.
Okay.
Let us say I tuned it at 600 millivolts. Then how many cells would I need?
Okay. I have tuned it. Okay. Now.
Then you will need 6 cells.
Okay.
Hai na?
Yes.
So it is how I tuned this cell, this inverter there. Okay. So depending on how you tune the inverter, you will need to change the number of cells you require.
Okay.
So this path, the number of cells which are selected by the replica word line over here, that should be programmable. I should be able to change the number of cells by just removing a little bit of metal one or something like that. Okay. So those projects which design the replica bit line or replica path, we talked about it in yesterday's office hours also. You have to take care of that. The cells are programmable. The word line is programmable, and whether it goes to VDD or ground, that should also be programmable.
Sir,
okay. Yes.
Sir, how will you replicate this bit cell, sir, exactly? I mean, I didn't understand how are you doing that? I mean, keeping the same type of...
I just repeat the cell.
Okay, so sir, just repeating the cell means, okay, I do understand layout wise, I do understand that we can place the same layout over there. But this cell which we have should be the worst case, right? And we'll be replicating the same cell all over my memory cell, right? So how does that make a difference actually?
It doesn't. Replica bit cell is supposed to look exactly like the real bit cell.
Yes, sir. But I mean, the bit cell which we use should be the worst case, right? Worst case bit cell in
You
replica.
have to qualify the worst case bit cell. Be careful. We have to qualify the worst case bit cell, but in the replica bit line, many cells would be there and they will be selected in parallel. So you cannot really have the worst case cell there. You just put a replica cell.
Okay, so
okay.
Okay, sir. Yeah.
So what to take care of the worst case cell, what you may do is you may want to tune the inverter at the replica bit line at a still lower voltage, so that you need to discharge still more.
Sir, regarding this inverter, sir, what are the conditions for tuning this inverter?
What are the conditions for tuning this inverter?
Yeah, means how you decided 700 millivolts. Replica.
Okay, I decided 700 millivolts because I wanted to keep more delay, let us say. Okay, I wanted to have bitline capacitance to play some role in my determining my timing. If I had kept this thing at, let us say, the trip point at, let us say, 0.7, so only 300 millivolt discharge was required. So the bitline capacitance would have a lower role to play in determining how much delay is added. Are you able to see this?
Okay.
So it is about what kind of impact I expect because of bitline capacitance versus wordline capacitance. Okay. Raghav, you have your hand raised.
Yes, sir. So I mean, I had a question. See, when we are thinking how many replica cells I should put in a replica orbit line, then I'm only considering the discharge, right? Discharge time ki 100 millivolts. So, but for example, like once I get off the inverter, the sense enabled signal, when it will reach, that will also depend na, ki sense amplifier is of the like the leftmost cell or the rightmost cell. So that delay is also coming picture.
Yeah,
But
yeah. So you
that
have to consider everything. I'm just giving you a very simplistic view here. If I give you the complex view right here, तो आप लोग अपने बाल नोचना शुरू कर देंगे. That's why I'm
Yes,
giving you a
sir.
very simplistic view. Even
Yes,
this
sir.
is complex for you, is it not?
Yes, sir.
So that is why.
So, but that is also taken care by the programmable bit cells only, the
Yes.
replica bits. Okay.
Yes. You just, if you want more delays, you reduce the number of cells which would discharge. Automatically, it will take longer to discharge. If you want to you want SIN to arrive faster, you just increase the number of cells. Automatically, the discharge would be faster.
Yes, sir. Yes.
Okay. So, what does this mean? You remember this timing diagram? Remember we talked about replica word line then also? तब आपको समझ में नहीं आया होगा. But now I am formally introducing it to you. When the replica word line comes, after some time reset comes. And that is what then resets the memory and makes it available for next cycle. So you cannot really have a reset come far away. Okay. And just like for the read cycle, you have a replica write bit line and a write detect circuit also there, which generates the reset. So difference is, in read cycle, the replica bitline discharge would directly generate the reset, whereas in a write cycle, there is an additional signal which is called as write detect. You want to ensure that the write operation has completed inside the memory cell, which would generate the reset. Okay. And then once the reset comes, then the same behavior is followed, but there is an additional observation that you have to make before you reset the memory in write cycle. Okay. Any questions?
Sir, why do we need write detect? Because we can just run a simulation where we can identify what's the worst placed bit cell, how much time it takes to write, and then after that automatically.
Yeah.
Write.
So what happens if it is a fast slot? Do you want to leave that kind of delay even in a fast slot?
No. Okay. Right. Got it.
You want to track something. That's why write detect also. Anything else?
But sir, when we are detecting write detect, that can cause stability issues because if you're reading it, right?
So write detect would come from the right replica bit line.
Okay.
Not really worried about stability then.
Okay.
So now अभी तक हमने SRAM और sense amplifier के अंदर mismatch की बात करी थी. Now we are also talking about the importance of matching and mismatch at the various other levels. We are saying that replica array and array should be matched, that the diffusion and metal profile has to be maintained, something that we were talking about in the beginning of today's class also. That RODEC and replica RODEC should be matched. Again, same diffusion and metal profile. Ensure similar WPE, STI and other effects. ensure similar IR drop. Now, what to do about aging? We not talked about aging, but yeah, this is something which still needs to be solved as a challenge. Okay. Then between word line and IO clocks or SAEN, they have to all run in the same metal layer. I remember having seen a failure in a big memory where the two match signals, one was running in metal 1, the other one was running in metal 3. As the production started, we observed that many lots were failing because of memory. And then we realized, oh, the match signals are running in different metal layers. See, metal layers are all drawn in different steps. Metal 1 could be of a different width and could see a different width and height, whereas metal 3 can see a different width and height. Even if the material is same, they could have different statistical positioning or different width and height across different metal layers. So if you want to match signals which could be run in different metal layers, always draw them in the same metal layer so that effect of RC is similar. In terms of doing the statistical analysis, Monte Carlo simulations is something that you already know about. But just to qualify 6 transistor memory cell within 1 sigma range, you need 30 to 50 simulations. If you have to go to 6 sigma qualification, you will need billions of simulation. This is prohibitive. You cannot really have that kind of a design time. So there are other methods which have been introduced, which are not just brute force Monte Carlo simulations. There is something called importance sampling, which is already implemented in ELDO. And there is something also which is called as design of experiments, which I think is also now getting implemented in Synopsys tools like SPICE, but I'm not sure. So typically ELDO is the most advanced tool, simulation tool till now, which has these advanced methods of statistical analysis also inbuilt into it. Okay, so some of you, if you work on some memory project with me, you may get to work on design of experiments if you're talking about weak bit testing or something like that. But otherwise, Monte Carlo is something that we will most commonly use. Okay, yeah. So any questions?
Sir, could you explain more about this importance sampling and design?
Okay, so importance sampling means that, okay, I tell the simulator that I want to measure, let us say, write time. And I tell it that larger write time is the risky thing for me. So in the simulator will run first 100 simulations with completely random distribution on its variables. Okay. And then it will start to observe some trend analysis. It will do some trend analysis and it will say that, okay, when I move my variables in this particular direction, that is when the write time increases. So whether there will really be failures or not, to estimate that, let me select more samples of that kind only. So it is kind of you doing some kind of machine learning while running the simulation and then choosing samples such that the probability of their failure on CAD is higher. Okay, so now to qualify 6 sigma, you do not need to run billions of simulations. Possibly 10,000 simulations will help you arrive at the worst case cell, because you're gravitating towards the worst lot, towards the worst place where the failure could happen. Is that okay?
Yes, sir. Sir, the worst case lot means, sir, don't we have a specific lot that is worst actually? I mean, for slow, we do know that, okay, at this point
Again,
or
when
at
I
this
say, okay, so sorry for that. When I say lot means a vector, worst case vectors. Okay. Different variations on VT of different devices, different variations on resistances, and so on. What is the worst case combination at which you will see the worst case result? That is what you are able to emulate much faster than in a regular Monte Carlo simulation. Okay. So lot did not mean that lot. With lot over I meant combination of various shifts. Okay. Now design of experiments, you can do the same analysis which would require 10,000 simulations with important sampling with possibly 1,000 or even less than 1,000 simulations. What you do in design of experiments is you say that, okay, I know that pass gate needs to be slow and pull up needs to be fast for the worst case right margin. I know this.
Yes, sir.
I say that I will myself inject 4.5 sigma variation on the pass gate and 4.5 sigma variation on the pull up. The pass gate will go towards the slow side, the pull up will go towards the fast side. So if I put 4.5 sigma variation on one and 4.5 on the other, what have I done? 4.5 square plus 4.5 square. If I add this, I will arrive at something like 6 sigma. So I am arriving at 6 sigma root mean square variation by putting 4.5 sigma variation on the pass gate, 4.5 sigma variation on the pull up. And if that particular simulation passes, I say, okay, my overall design is 6 sigma qualified.
Okay, sir. Got it.
This is much lesser number of simulations than important sampling. Do you see that?
Yes, sir.
But now you have to apply your brains as a designer.
But sir, design of experiments isn't that specific towards the thing which you do for, I mean, like
yes.
For right, it's specific. For another operation, it might be specific.
Yes. यहीं पे आपको दिमाग लगाना है.
Okay, sir.
A fresh engineer who has not understood the design well cannot do this. You need expertise to even run design of experiments because you know what you have to know what experiments to design.
Yes, sir.
Okay. And do you realize that for a memory cell, when I have understood right margin, it is so easy to design. But think of implementing it for the self-timing paths. Can you design it? Can you distribute how much variation to put on which cells, which devices of which cells? Can you do that? No.
It's hard.
So design of experiments can only be done on very small circuits, small sets. Okay. For large paths, lots of devices where variations could be distributed, you prefer to go to important sampling or brute force Monte Carlo.
So with this example, the design of experiment, you took the 4.5 sigma with considering the right
margin
operation. So, but like, when I qualifying for example, a bit cell, I will have to qualify for all the FMs, right?
Yes. So you will run a different design of experiments for SNM, a different design of experiments for read current. You'll have to do those design everything separately. Anyway, the PVT at which SNM is worst is different from the PVT at which write is worst, is it not? You anyway have to do a different analysis. You have to have a different stimuli. So it's okay. Not a big deal. Okay.
Can you move to previous slide? Sir, I mean, इसमें replica array क्या चीज़ है सर? I mean, और इसमें सर दो चीज़ थी कि diffusion profile का मतलब क्या है सर?
Active profile, how like the stress effect on the active should be same. So what does profile mean? What do you understand by the term profile?
So profiling का मतलब पता है मतलब कि you are basically putting different two categories, some kind of like a bin. You are profiling in certain.
That is classification. That is. So profile means profile means the boundaries are the same. You know, the behavior or the environment. Let us say, you know, metal profile. आप कह लो metal design and environment. They have to be similar. Okay. So if you have made this kind of structure in your actual cell, you should make the similar kind of structure even in your replica cell. Okay.
अच्छा, okay, okay. Diffusion और metal दोनों same होगा यहाँ पे हमारे. तो सब कुछ same.
That is what it means. This is also called as structural matching. Okay.
Okay.
Anything else? Okay, so we will close the class here and we'll meet next on Tuesday.
In design of experiments, we are basically versioning the suppose gate or device. So that means we are hacking into the library and changing the VT.
Yes, so Eldo allows you to do that by not going into the model file.
Okay.
XSpice and Spectre do not do that yet.
Yeah. Okay.
Okay, and also to be able to do that, you should have the models which allow you to do that. The model should be defined in such a way that you are able to do that from outside, not going inside.
That means the Foundry should give us a feature.
Yeah. So till the time Foundries did not give us the feature, we used to do the same thing by artificially increasing the length and width and so on.
Okay.
Not a good thing to do, but yeah, that was how we used to do it earlier.
Okay.
Okay.
Thank you.
All the best, guys. See you. Yeah.
What was the question, sir? Actually, I have had a net issue, so.
No, don't worry. That Dipank has some prior experience of memory design, so he was asking that to be able to do design of experiments, you need to be able to change the VT of the device.
Okay.
Can you change the VT of the device in your simulations, Vaishnav?
Sir, I mean, there is an option in schematic. I can change it. I mean,
Oh, that is HVT, LVT, and that only. Now, can you change it by 4.5 sigma?
I don't think, sir.
Yeah,
No, sir.
that was what he was asking. How do you do it? I was explaining that to him.
Okay.
Okay. Yeah. Chaliye. Okay, guys. All the best. See you in the next class then. Hello.
Thank you, sir.
Yeah. Bye-bye.